Dear colleagues, dear friends, this is Dr. Necati Fındıklı, and together with Dr. Fadi Şüker, we hereby have the privilege to start this exciting webinar, which is the first of a series jointly organized by Turkish Society of Clinical Embryology and Middle East Fertility Society's Special Interest Group of Embryology. And on behalf of the organization committee, we are very happy to welcome you tonight to this very exciting session. And the main idea of this webinar series is to provide an exciting and stimulating platform to increase the knowledge and cooperation of clinical embryologists or reproductive scientists working in the region. And we hope that we can reach this goal by covering important as well as controversial topics that we face in our daily ART or IVF practice. And the topic of tonight is the clinical and laboratory aspects of artificial oocyte activation. With two distinguished speakers and four panelists, we will be diving deeply in this matter, discussing tips and tricks of its use in our lab settings. And we will be more than happy if you also can share your questions and comments on the YouTube channel Q&A box, which is located on the right side of your screen. And I wish you a very successful webinar. And I would like to now pass the microphone to my dear colleague, Fadi, to present the speakers.
Okay, thank you, Necati. On behalf of the Middle East Fertility Society, also it is my honor to officially welcome you to this joint activity between MEFS and KED. As Necati said, this series of activities gonna be a great night for learning, for connecting, and for aha moments. So tonight we're gonna present two talks about oocyte artificial activation. And our panelists, Nagam Yunus, Alia Hourani, Halil Russo, and Kerem Dirikam will discuss your questions at the end of the talks. So let me introduce our first speaker, Dr. Evrem Unsal. She's an associate professor, graduated from the University of Ankara in 1997. She completed her PhD at Ankara University Biotechnology Institute in 2007. She has been working as an associate professor in the Department of Medical Genetics, Faculty of Medicine, Yüksek İhtisas University. Dr. Unsal has been working as a laboratory supervisor at GenArt IVF Center since 2002. She currently manages the Molecular Genetics Laboratory at Microgen Genetics Diagnosis Center, and her major interests in research are PGT, exome and genomic testing, and analysis of rare genetic disease screening with NGS. Today, she will talk about pulse-stimulated electrical oocyte activation, a path to improve IVF success. Dr. Evrem, I welcome you, and the floor is yours.
Thank you, Dr. Fadi. First of all, I would like to thank the Clinical Embryology and Middle East Fertility Society Board for their invitation. It's an honor for me to be the same stage with the expert, Dr. Thomas Ebner, and I'd like to share our 15 years of experience regarding oocyte activation. Okay, firstly, I'd like to mention about the principles of oocyte activation. Oocyte activation is a spatially and temporally orchestrated process. Critical endpoints include resumption of meiosis II, second polar body extrusion, cortical granule exocytosis, and cytoskeletal rearrangements. It's generally accepted that the oocyte activation in mammals is a complicated and spatial temporal regulated process triggered by the entry of the sperm. Several minutes after sperm oocyte plasma membrane interaction, intracellular calcium oscillations flowing from endoplasmic reticulum are induced by the release of soluble sperm factors named phospholipase C-zeta. I will say it as PLC-zeta from now on. And oocyte activation deficiency is one of the major causes underlying failure of ICSI cycles. Defects in calcium release mechanism are associated with most oocyte activation defects. The process of calcium release can be clinically mimicked via assisted oocyte activation. And the well-established and most commonly described activation protocols can be classified into 3 different methods: mechanical, electrical, and chemical stimuli, which artificially promote an increase in the levels of intracytoplasmic calcium. However, concerns regarding safety and efficacy underlie potential risks that must be addressed before such methods can be safely widely used. Mechanical activation usually involves a disruption of the plasma membrane or components within the oolemma, leading to an elevation of calcium within the oocyte due to influx of calcium and disruption of calcium store membranes of endoplasmic reticulum. The mechanisms underlying chemical activation vary on the type of agent utilized, but usually involve the facilitate transport of extracellular calcium into the oocyte, either directly or via transport channels. Electrical activation usually involves the direct application of a voltage current, inducing charged lipid bilayer, protein migration, and pore formation in the membrane, enabling extracellular calcium influx into the oolemma. Various mechanical activation methods are described in the literature, but we have to keep in mind that conventional ICSI on its own has oocyte activation potential. Some data from literature suggests that the modified ICSI technique can give better fertilization in patients with a history of total fertilization failure or low fertilization. Vigorous aspiration of cytoplasm and different position of the pipette tip is supposed to increase calcium levels during injection. And aspiration of cytoplasm also enables better contact of sperm with intracellular storage of calcium. Additionally, modified techniques enable mechanical disruption of endoplasmic reticulum during the movements of the microinjection needle in the oocyte cytoplasm. Dr. Thomas Ebner has a lot of experience with mechanical and chemical activation, so I will focus on electrical activation during the rest of my speech. What are the indications of assisted oocyte activation? TFF cases are obvious targets. If we need a definition for TFF, TFF is generally described as recurrent fertilization failure in all oocytes for subsequent cycles. For standardization's sake, we can define TFF as cases in which fertilization was not observed in at least 2 previous IVF attempts with more than 5 mature oocytes and optimal sperm concentration. TFF can reoccur, and the incidence of TFF cases is around 1 to 3%. TFF occurs due to the defects in oocyte activation, which allows us to bypass this defect by assisted oocyte activation. Thus, TFF cases get the most advantage out of activation techniques. Extended assisted oocyte activation indications include low fertility rate, severe male factor like globozoospermia, round or elongated spermatid injection, cleavage arrest, rescue ICSI, and PLC-zeta depletion in sperm. And nuclear transplantation has been also one of the major indications of oocyte activation. Whether sperm or oocyte born is the main cause for TFF, resulting in the inability of mature oocytes to undergo activation and complete the fertilization by sperm. I'd like to tell our story about electrical oocyte activation in our clinic, which started in 2007. In these years, electrical activation of oocyte was a hot topic, with cloning experiments making Dolly a superstar for that period. This made electrical activation popular, and its further use was investigated by many researchers. BTX instrument was used predominantly in this field. Oocyte enucleation and nuclear transplantation trials were performed in cases with advanced maternal age, and electronical activation was mainly used for fusion events. Additionally, animal experiments suggested that electrical stimulation triggers calcium influx by creating micropores on the membranes of the somatic and gamete cells. This was interesting for us. We decided to investigate potential use of electroporation for oocyte activation. We have decided to purchase BTX instrument, which was used in Dolly experiments, and since no distributor was available in Turkey at that period, we have contacted directly to its manufacturers and persuaded that to sell us the instruments, since they were all curious why we need to BTX at that time. Of course, it was long optimization period. We tried to find optimum time and electrical current to activate, but not to harm the oocytes. Preliminary results in TFF cases have encouraged us to pursue these investigations. I'd like to describe the optimized protocol here. Piezoelectric stimulation was applied 20 minutes after microinjection with Zeus electromanipulator at room temperature with a chamber with 2 stainless steel electrodes filled with activation buffer. Injected oocytes were activated with a single pulse, which lasted 100 microseconds, and the conventional embryo culture protocol was followed. By applying direct electrical current within Petri dish with oocytes, the electrical field stimulates charged proteins to move toward the plasma membrane. This leads to an increase in the number of pores of plasma membrane, calcium conductivity increases, and more calcium enters the oocytes from the surroundings. There is only one large calcium concentration increase with this protocol. I'd like to share a video from our electrical activation protocol. We have to wait for a while. Now you are seeing the moment of electrical stimulation. Here you can observe cytoskeletal movements and morphological changes on oocyte membrane. IVF centers who were aware of piezo application were sending the oocyte to our laboratory with a transport incubator after ICSI, and we were delivering the cells to them by making electrical oocyte activation. Centers outside the province were preparing the patients and directing them to our laboratory on the day of oocyte pickup. For this reason, Professor Baltajo, owner of our company, produced a device that can only be used for oocyte activation and pioneered the spread of piezo application in this context. In 2009, we published our first data about ICSI combined with piezoelectric stimulation in infertile couples having a history of total fertilization failure. In this study, we applied piezoelectric stimulation 20 minutes after sperm injection. The patients were allocated to 2 groups. Group 1 included 21 patients with only 1 previous TFF, and Group 2 included 50 patients with more than 1 previous TFF attempt. In Group 1, combined ICSI with piezoelectric stimulation was applied to 123 M2 oocytes, which is Group 1A, and standard ICSI was applied for the remaining 88, Group 1B. In Group 2, all the oocytes were subjected to ICSI with piezoelectric activation. We obtained 62% fertilization rate in Group 1A compared to 12% fertilization rate in ICSI-only group. In Group 2, 49% fertilization rate was observed, We have to keep in mind that these cases had recurrent TFF cases, thus 50% being lower than 62% in group 1A is expected. Nevertheless, this was an encouraging ratio. In the same year, a study of Mansour and his colleagues was published in Fertility and Sterility. The aim of the study was to estimate the value of the electrical activation of oocytes in patients with previously failed or limited fertilization after ICSI, as well as in patients with possibility of failed fertilization as a result of teratozoospermia. They performed electroactivation of oocytes after ICSI for 10 TFF patients. They also used piezo stimulation for 241 ICSI cycles for infertile couples with severe oligoasthenoteratospermia or azoospermia and abnormal sperm morphology or totally motile sperms. 46% fertilization ratio was achieved in TFF group. Sibling oocytes of low fertilization group was divided into two groups. Fertilization rate of piezo combined ICSI was 68% and 60% in ICSI-only control group. We published our second study with additional data in 2014. In this study, 6 different patient groups were evaluated: testicular elongated, tessa-immotile, tessa-motile, severe oligozoospermia, totally motile, and low fertilization failure cases. In those years, ICSI was applied in many azoospermic cases where sperm could not be obtained. We were able to achieve pregnancy in only 1 out of 43 patients in our applications to demonstrate the effectiveness of electroporation in these cases. Despite the revival of applications for round spermatid injection with electrical stimulation, we have chosen not to perform ICSI with round or elongated spermatids in our clinic for many years. The fact that these applications does not have satisfactory success rates imposes an unnecessary economic and emotional burden on the patients. For this reason, this approach is not candidate for routine use in clinic, even though they are performed in very high number of patients nowadays. You can see fertilization and clinical pregnancy rates for other groups on the table. I will not focus on these due to small sample size. I will also share a more updated data in the following slides. In addition, I'd like to briefly mention the results of study conducted with electron microscopy to examine the effects of electrical activation at the organelle and cytoskeletal level. We did this work as a master thesis of one of my students. In this study, we investigated the ultrastructural structure of the oocytes in which chemical method and electrical activation were applied. Organelle damage and differentiation in the mitochondrial membrane were observed in the chemical method. On the other hand, there was no effect on the cell membrane and especially on the mitochondria in oocytes where electrical stimulation was applied. Electrical stimulation has been around for more than 20 years. Yanagida and his colleagues were the first to use piezoelectric stimulation for human oocyte activation in 1999. In this study, they placed oocytes between 2 parallel electrodes in an electric chamber 30 minutes after ICSI procedure. They obtained a live twin birth in one of these 3 cases. As mentioned before, I wasn't share our updated electrical activation data. The patients are divided into 4 groups: TFF group, globozoospermia, totally motile, and low fertilization. Average maternal age was around 32 for 4 groups. I will focus on each group independent data in the following slides. In TFF group, 29 patients were evaluated. Fertilization rate was 39%, but 7% of these cases had abnormal fertilization. In 31 of cases, embryo transfer was performed, resulting in 67% pregnancy rate. We can clearly see that once fertilization problem is bypassed, high pregnancy rate can be achieved. In global group, we evaluated 29 patients. Fertilization rate was 39%, and abnormal fertilization rate was 3% of these cases. In 66% of cases, embryo transfer was performed and 23% pregnancy rate was achieved. Sorry, let me try to go back. Fertilization. I'm sorry. This is total immotile group. The headline is not correct. I am aware now. In total immotile group, 40 patients were evaluated. Fertilization rate was 60%, but 12% of these cases had abnormal fertilization. This group of cases have the highest abnormal fertilization ratio among all. In 55% of cases, embryo transfer was performed, resulting 23% pregnancy rate was observed. Finally, in low fertilization group, we also evaluated 40 patients, and low fertilization in this group is defined as less than 30% fertilization in their previous cycles, and fertilization rate was 41%, but 8% of these cases had abnormal fertilization. In 59 of cases, embryo transfer was performed, resulting and 18% pregnancy rate was observed. Once the data is put all together, we can conclude that high pregnancy can be observed in TFF cases once fertilization problem is bypassed. In other three groups, we observed a high embryo transfer operation rate, which is around 65%, but low pregnancy rate compared to TFF group. This suggests that other parameters are crucial as fertilization in these cases, which can limit high pregnancy rates. Sorry. The high success of TFF cases can suggest potential oocyte defects can be more effectively overcome by oocyte activation compared to sperm-associated defects. I also would like to mention about the consideration of assisted oocyte activation efficacy and safety. In the recently published review, these considerations were evaluated in details. The first handicap is heterogeneity in study groups. In the case of chemical activation, there is a significant variety among chemicals used, chemical concentration, timing and duration of exposure, and number of times the chemical is applied. Exact concentration remains undisclosed by the manufacturer or researchers of either laboratory-generated chemical activators or commercially available options. There is also variety in electrical assisted oocyte activation methodologies. Variance in the types of electrical pulses, time duration of pulses, and repetition rates of pulses all contribute to heterogeneity of these studies. On the other hand, inconsistent sample inclusion criteria is another handicap. Immature testicular sperm may require exposure to higher levels of activating compound than ejaculated or epididymal sperm. Due to a dearth of embryos and the ethical considerations, data from previously failed ICSI cycles are employed as controls in many efficacy and safety studies, or sibling oocyte split randomizations have been evaluating. Restricted sample size is also a big limitation, as assisted oocyte activation is only recommended for only select patients. This severely restricts the availability of embryos for efficacy and safety assessments. Thus, although a large number of studies have been conducted, each has a small sample size, additional difficulty establishing optimal control groups with randomization. Therefore, multi-center study design is highly important for standardized assessments. Animal model limitations are also another drawback in which numerous differences exist between oocyte activation mechanisms of humans and animal models, It's tough to obtain consistent results and implement animal model findings to human studies. There are accumulating data on safety of these methods. In the recent study of Ghent, she analyzed neonatal and neurodevelopmental outcomes of 21 children born after cycles with assisted oocyte activation. As a consequence, they found mean outcome within the expected ranges. Some studies revealed no physical or mental developmental disorders associated with babies born through these procedures. As a conclusion, assisted oocyte activation remains the end-of-the-line treatment option. Further research on the efficacy and safety is required, and establishment of an internationally recognized set of guidelines mandatory, and standardized protocols, clear criteria for patient inclusion and subclassification, list of mandatory endpoints that can be universally used, and multi-center studies and international cooperation between different fertility centers would be preferred. Assisted oocyte activation appears an immensely promising avenue of treatment for not just oocyte activation defect and TFF, but perhaps even to improve the efficacy of ART overall. However, nature has regulatory mechanisms to eliminate errors, and when we force events that would not happen spontaneously, it's always important to verify all possible negative effects of such procedures. I'd like to thank to my colleagues and Professor Baltejer for their great support, and thank you for your patience.
Thank you, Dr. Evren, for this insightful presentation. So we will keep the questions till the end of the session. So let's move on now to the next talk. So it's an honor for me. It's also an honor for me to present our next speaker, Dr. Thomas Ebner. Dr. Thomas graduated from the University of Salzburg, Austria in 1992. He completed his doctorate and postdoctoral thesis. He became a university professor in Linz, Salzburg, and Graz. He has published more than 160 papers and book chapters as first and co-author. His research interests include artificial gamete activation, time-lapse imaging, non-invasive IVF selection processes, and culture media. He was certified as a senior clinical embryologist by ESHRE in 2008. He was executive board member of both Alpha, Scientist in Reproductive Medicine, and ESHRE, and currently is active in ESHRE committees for certification of clinical embryologists and ART centers. Dr. Ebner will present today tips and pitfalls in ionophore application. The floor is yours, Dr. Ebner.
Thanks, Fadi. I hope you can see my screen now. Can anyone
tell your slide?
Okay, fine. Well, then I'm gonna start. And I'd like to start saying thank you very much for this privilege to be part of the first conjoint meeting of the MEFS Special Interest Group Embryology and the KED. So I was involved in a KED webinar earlier this year, also in one last year. And I was a little bit afraid about the topic, but once I heard that it's be a little bit more focused on technical aspects, I was quite happy, because this is something that is usually pretty underestimated. And I hope I can share some tips and pitfalls with you, and maybe something of that is new. And I also would like to thank everyone for this wonderful talk. I always was a little bit afraid, and I used to say that electrical activation is part of a Frankenstein lab, but it's not, obviously. I did not know that you work at this topic for 15 years now, and that the gadget actually is a very tiny little one, and there is almost no knocks here. So happy to discuss it later on. So I'd like to start with my conflicts of interests, which you can see here.
Sorry, Thomas, it's not a full screen. So yeah.
It's not at full screen?
Yeah.
Okay, so let me see. Does it work now?
No.
Okay. Maybe I stop sharing and,
Yeah.
and redo it. So I have another conflict. I'm not able to do it in a technical way. So
Meanwhile, I encourage all the audience to ask their questions on the chat box and to hold them till the end of both talks.
Fadi, I copied and pasted in Arabic, but I'm not sure what I meant by it.
Yes.
So can you check it on the chat box?
Yeah. Perfect.
is it better
Still,
now?
no, still we see all of the slides in a one screen.
Okay, well, that's not what it's supposed to,
So
but it did
slideshow
work before.
on the bottom.
Pardon?
Thomas, can you close this window and open it again and minimize, go for sharing slides on the top and minimize the first slide, and then you can share it. Minimize the first slide.
Minimize the first slide.
If it's okay on your screen, maybe you can just share your screen, Thomas.
Like go
Not the
for
part-
slideshow
yeah.
mode.
And then
Is it
slideshow.
now?
Great.
Yeah, it's
Is it-
much better now.
Okay, so it's full screen now.
Yes.
Okay, so
Slideshow.
No.
You need-
Still, you can go for the option of
the
share
slideshow.
slideshow
Yeah.
on the top.
Yes.
This one?
Slideshow from the
Yes.
beginning.
Yes. Yes, please.
okay.
Just to remove the left line, you can go for slideshow from the beginning. I think after animation,
Is it now a full screen?
No.
no,
Oh, what a pity.
it
So how
shows
do
the
we
slide.
proceed?
But we can still see the
Yes,
slides.
yes, yeah. You can go to the left icon, to the most left icon, and
This
to
one.
start. Yes,
Yes.
to start from the beginning. Yes.
It's not taking.
What do you see now? I think it's still the same problem.
time.
Yeah. Or maybe you can just minimize the left side, then you can move one by one. Yeah.
Yes.
So like that?
Yes. Yeah.
Yes.
So we can
Great.
continue like this
Yes.
to save the
Okay,
time.
I'm so
Yeah.
sorry.
No problem.
No
Not sure
problem.
why it doesn't work because it did before.
There is an
Anyway.
idea from the audience. It says that press F5.
F5, which I did now.
Didn't work. Anyway, okay.
We can
We're
see
fine.
the slides.
Yeah.
We're fine.
Okay, then we go with the slides. Okay, now you have had plenty of time to see my conflicts of interest. Only the one highlighted, I guess, is of relevance because this is the German company producing the ready-to-use ionophore. The rest, more or less, is not of importance here. So I also have some introductory slide like Evrim did, and this slide should show you that oocyte activation actually is only one process, but the most important one on the way from gamete stage to zygote stage to the fertilized oocyte. And you can also see here that in terms of the male gamete, actually, it has to undergo a certain cascade of processes that makes it fit for fertilization. And on the other hand, the oocyte has to have the nuclear as well as the cytoplasmic maturation in a very coordinated way, in a synchronized way, to give the best outcome. And once those two gametes are actually perfectly mature, I would say, then it starts the fertilization process. And what we have physiologically is an oscillation calcium pattern. As has been shown by Iriam, that this calcium comes from the smooth endoplasmatic reticulum within the cell, and it's in the form of calcium oscillations. And this is of particular importance because it needs oscillations so that the calcium signal can be transported over a longer time. And actually the area under the curve, under those spikes, represents the calcium that is available for the cell. And there is the stimulus, as already has been shown, so the sperms enters the oocyte. It brings in PLC theta, which is the sperm-derived oocyte activation factor, and via inositol 3-phosphate, it then recruits, which this binds to its receptors at the smooth endoplasmatic reticulum. It recruits calcium that comes into the cell. So, but this is only the on mechanism. So this is only one part of relevance. But the oocyte has to have a system to deal with depletion of calcium. So if the calcium gets short, then definitely there are some mechanisms. Two of them are STIM1 and STIM2, but also ORA1, which is located on the O-lemma, and they detect calcium depletion. So if it's a mild form of depletion, STIM2 will act, and if it's a severe form of calcium depletion, STIM1 will migrate towards the O-lemma to open the channels for ORA1. And then calcium comes into the cell and refills the storages. So this is one mechanism, but it's exactly as important to have or to bring back the calcium to zero, because this then will guarantee that there is no feedback mechanism, so that the signal definitely gets new all the time. And therefore the calcium has to be put to mitochondria or off the cell. And here you see the PMCA mechanisms that help for that. So this is the physiological way. And this is such a complex, complicated complex, so that you can see, sorry, here we go. That the slight mutation in male gamete, and even more important in the oocyte, may cause dramatic deficiency in fertilization potential, so to say. So definitely, once one of the gametes has a problem in a genetic way, then it won't work. So we have to recruit then calcium from other sources than from the smooth endoplasmic reticulum. And this is possible by either getting it from the extracellular part, which has been shown by Iriam before, but it could also help to deplete it mechanically or by rigorous activation from the endocytoplasmic storages. So two ways to recruit calcium and to use it. And the methods to do so have already been shown before. It's the electrical activation technique, and they also mentioned mechanical activation, but I'm going to talk today on the chemical activation. And chemical activation means one of these compounds. Could be strontium chloride, 6-DMAP, 4-bol esters, thimerosal, and mostly calcium ionophores are used in IVF labs. Some of those, or most of that, are less effective in human oocytes. They are limited to some species, and so they don't work in human at all, or they may cause meiotic spindle disruption. This means we have to rely on the more safe agents, I would say. And calcium ionophores have been tested in great detail before. So why do ionophores work at all? If you see here, there's only one single peak. So no way, no single oscillation pattern comes from an ionophore. And the reasons are here in red. So the good thing is that the downstream events, like the calcium calmodulin dependent kinase 2 activity, raises and falls with the initial calcium peak in a directly proportional manner. This means the larger the first peak is, and there is only one peak, the more likely the cell gets fertilized. And once activated, autophosphorylation of ChemK2 may keep the enzyme active even without the presence of calcium at all. meaning it is somehow self-driving. And any reduction in the first calcium peak or in the frequency can be compensated by both a higher amplitude and a longer total duration of the same, meaning the area under the curve has to go up, meaning more calcium is available. And it seems that mammalian oocytes are very tolerant to perturbations in calcium oscillation patterns, as long as the total amount of calcium release is uncompromised and passes a critical threshold. So which ionophore should we use then? So we have two possibilities. Both look quite complicated. One comes from Streptomyces catarrhaensis and the other one from Conclopathus, meaning so they have antibiotic activity. And on the left side, you see the calcimycin, or also referred to as A23187. And on the other hand, you see the ionomycin. So which one should we use then in IVF? There are differences, and since these are not animated, the slides now, you have to, I hope you can see my cursor. But what I'd like to show here is that calcimycin is not very specific for calcium, although it's more or less in the name. So manganese would be the most potential cation that could bind to this ionophore. So calcium and magnesium are also pretty good, but strontium and barium are not. So this is calcimycin. On the other hand, we have ionomycin, which has a much higher binding power to calcium itself. So this is definitely a benefit. And it binds in a 1-to-1 ratio. So there's one molecule of ionophore, of ionomycin in this case, binds one molecule of calcium. And in calcimycin, it needs two molecules of ionophore to bind one molecule of calcium. And definitely this has something to do with the concentration. And ionomycin in theory and also in practice, as we know, meanwhile, is more effective. And this has been shown by this nice work from Nikiforaki from the Ghent group. And it shows that the calcimycin gave a lower area under the curve as compared to ionomycin in human oocytes donated for research. Irrespective of the ionophore that we plan to use, we have to make sure that we use the proper indication. This slide has also been shown before, at least in part. So incomplete fertilization failure in previous cycles definitely is no option to do ICSI again over and over. So you have to do something. The patient requests something new, some adaptation of the protocol, and artificial oocyte activation would be my first choice in case of complete fertilization failure. But also, as has pointed out earlier, 30% fertilization rate may serve as a threshold to use ionophore or not the next cycle. It is also used in severe male factor like azole and tryptospermia and in frozen sperm as well. If there is a developmental problem in previous cycles, this is a tricky thing, and in the next slide, we're going to discuss this a little bit. But there are also some contraindications, meaning indications, patients in which or in who you should not use ionophore, at least not the calcimycin. And this is the globospermia. There are case reports that calcimycin worked, but ionomycin does better. And what I learned today is that electrical activation actually works even more better, or even better. In cases of low ovarian response, of course, is no use to work with an ionophore, because if you only 1 or 2 oocytes, it's also a problem of statistics to get fertilizations or not. I would not use it in SCR positive eggs. Those eggs that has the dysmorphisms of the smooth endoplasmic reticulum cluster have all the calcium concentrated in this cluster, and usually, or actually, it should be concentrated or distributed equally all over the cell. And this means it's not the first choice to use an ionophore. The same for immature eggs, as I will show you later on. So let's come back to developmental problems. You see that the first paper, bottom of the oocyte, is one of our studies that we used an ionophore and ready to use ionophore to bring up the developmental potential of embryos. And the idea behind was that calcium is also relevant for mitosis. And if you bring up the calcium, you may have better mitosis. And those embryos that arrest have been shown not to have calcium at all within the cell. This means calcium could drive mitosis. The only problem is it's not the perfect stage that you apply ionophore if you want to bring up mitosis. So colleagues from Egypt, they used it at zygote stage to cure more or less those cases that had complete developmental arrest at zygote stage. And recently, Xi and co-workers from China, they used it after 44 hours after ICSI to bring up mitosis and to get to blastocyst stage. So this would be more logical, at least to me, to apply it a little bit later, which we couldn't do because the ethical votum said that we have to do it the way it is published. And even more recently, there were two papers highlighted here in black, one from Belgium and the other one from China, and they did not find such an effect. In other words, ionophore, in one case ionomycin, in one case a ready-to-use calcimycin, did not improve cleavage rate. And for those of you who are interested, I may refer you to one letter that I wrote to JARC, a letter to the editor, where I tried to come to the point and explain why all those studies find divergent results. And I think it's definitely a problem. What is developmental problem? While we thought it's complete arrest in the previous cycle, the Belgian colleagues, for example, said if it's a 4-cell embryo on day 3. So there are completely different indications, and we mix up and we compare apples and oranges within literature. And this is something that we should keep in mind. So you better get your own idea and test it yourself. And the more homogeneous your study group is, the better will be the clinical value of the outcome. So speaking of ionophores, there are two ways to work with it. One way would be to use a homemade product so that you mix it your own in your lab. And the other one is to rely on the ready-to-use compound that is currently available. In Europe, and you see here the European Cells and Tissue Directives, they actually ask for CE certified products. The ionophore I'm talking about is only CE marked as an IVD, a DVD, but it's, or no, IVD, in vitro diagnosticum. It's not a class 2 medical product, not yet, I should say. So the company, I think, is working on that. But definitely, there is no recommendation of the tissue directives to mix it your own, but you can do so. But there are some pitfalls. For example, it's very hard to standardize the production, if it's not impossible at all. You may have sterility issues if you buy something that is not purified, or maybe it is purified, but during the process of mixing it, it could cause a problem. And also the quality testing is difficult in our labs. And even more importantly, the ionophore is not soluble in water at all. So it's hydrophobe, I would say. This means that you have to mix it with DMSO, with dimethyl sulfoxide. And we all know that at a certain concentration, this small molecule causes pathogenetic activation. So you should try to use not more than 1% of DMSO and mix it with the ionophore. And then you have to mix it with some medium. So some basic medium, and then you may have a topic which could be osmolality or also calcium, as I will show you in a minute. So it's not easy to mix it yourself, but people are doing it and save costs by doing so. Here you see that it also depends. So the effect depends on the concentration. Here we have ionomycin in a mouse model, and they used 5 micromolar, 10 and 50 micromolar. And what they did found is that increasing ionomycin concentration over a certain threshold showed no benefit. And on the other hand, calcium-free medium showed 0% blastocyst formation, which fits nicely to the hypothesis I've shown you before, because if there is no calcium outside the cell that could go in the cell by using an ionophore, definitely there will be no effect. And no effect in this case means no fertilization, no blastocyst formation. And these authors blamed the calcium pumps to be responsible for that. So the high intracellular calcium inhibited or damaged the calcium pumps. And this could be the reason why there is no use to use higher concentrations. For us, it's more important looking on culture media that we use in the daily life. And here you see, maybe I should not listed them, but I have no conflict of interest with all those companies. So Vitrolife, Quince, and Sage Medium, and left to the bottom, you see the calcium concentration in this media, and you see that Vitrolife and Sage have a much higher calcium content as compared to Quince CC medium, and this means that the calcium peak that you get using an ionophore is higher in these media. And interestingly, 5 micromolar ionomycin was not effective at all in all 3 groups. And the amplitude and the area under the curve was lower in human as compared to the mouse model that I showed you before. And there was a direct correlation between external calcium and the area under the curve. So one pitfall in mixing ionophore yourself is that there is a very high risk of choosing a too low concentration of the ionophore and the culture medium with reduced calcium. And you may not even know the amount of calcium in your culture medium. So let's move on with the ready-to-use GM508 cold active, as it's called. So this is a bicarbonate buffered ionophore. The shelf life is 6 months, provided that you store it in the fridge, and you should use it within 7 days upon opening. And definitely you should not freeze it in aliquots, because we tend to freeze products in aliquots that we don't need that frequently. But by doing so, and Markus Montag and myself, during our mouse studies, we tested it. It did not. It did change the effectivity. So you should not freeze it. On the other hand, it's guaranteed that all the quality control and quality management system is well working. So they did a sterility testing, endotoxin testing, and the mouse embryo assay. But you see, the range of pH is very broad. So 7 to 7.6. 7 is definitely not physiological. 7.6 is for the sperm. It's physiological. For the oocyte, most probably not. And this means that definitely the time within the ready-to-use compound should be shortened or kept as short as possible. Osmolality is 400 to 450. And you may take into consideration that we work with culture media around 260 to 300 or 290 milliosmol. If you have a culture medium with glycine in it, you may react, or you can work with 350 milliosmol without problems, or with little problems, but 400 to 450 is much too high. And it's hyperosmotic, which may cause shrinkage. And in case you see shrinkage of oocytes within the ready-to-use compound, then this might be an osmolytic problem. So shorten the time if possible. So the ready-to-use product here on top, it said, well, the word ready-to-use literally says, please do not dilute it. So I had one customer that did not complain, but asked for help. And since I'm a consultant, I asked how he did it. And he was, or she was actually diluting the ready-to-use compound 100 times with their own culture media. And logically, there is no effect at all after dilution. But let's consider that we use it as it comes out of the bottle. Then you see, you do your ICSI. You apply an ionophore, homemade or ready to use, for 15 minutes. Then you wash it 3 times. And then you go to the culture, 5 days. On the bottom of the slide, you see a copy paste scheme from the manual, from the leaflet from the company, showing that you should work with 30 microliter drops and with only 2 washing steps. And it's also recommended to agitate the vial before usage, or you steer it. And this is of utmost importance. Believe me, if you do not steer it, you may create a gradient, so that you have the ionophore to the bottom of the bottle and maybe the culture media on the top of the bottle. And then definitely there will be no effect. So please steer it a little bit before you use it. It's also recommended to pre-equilibrate it for 4 hours. And since this is a bicarbonate based medium, definitely there is no room for HEPAs or MOPS media, and no way that you culture it in a heating cabinet. What you need is an incubator supplying the egg with CO2 so that it's in a pH range that you want. It is also said in the leaflet that mineral oil is not necessary due to the short exposure time. While I would not be in favor of this acting, so I really recommend to use oil to avoid evaporation. And I also strongly advise you to use larger volumes than 30 microliter. So I work with 50 to 100 microliter covered with mineral oil, because this would allow, well, one thing is that you could avoid suboptimal culture conditions if you have culture medium at a higher volume and also a mineral oil, but you can also culture more oocytes. So in the 30 microliter drop, you should not bring in too many oocytes, because keep in mind it needs 2 molecules of ionophore per oocyte to transport one calcium ion. And there is indeed the observation that some dishes, and actually I don't know which, may favor the sticking of the oocytes to the bottom of the dish. So this is something that we have to find out in the near future. I never observed that, but I heard it from Spain and also from one colleague from the Middle East. So this is something that we have to solve in the future. And definitely, we do not use ionophore for all types of oocytes. So oocyte maturity is very critical to find the optimal time of ICSI in one case. But if you see here, from prophase 1 to metaphase 2, there's a change in the organization of the endoplasmatic reticulum, also in its number and in the being a cluster or not. And the endoplasmatic reticulum actually corresponds to the location of the receptors for the IP3, which means if this is not distributed equally over the cell, it may cause a problem. And if you would bring here an ionophore, then definitely you may, it's precautious artificial local activation, which may not end correctly. Thinking of the spindle that has been published by Björn Hendrik's group, you're seeing the disorganized spindles from a very special case, I have to admit. But nevertheless, I'd like to give you the tip that you do never ionophore treatment for immature eggs, so metaphase 1 or telophase 1, even if I suspect it to be a telophase 1 because the polar body is in a fova or so, I would not do an ionophore. I only take those that I'm sure that they are M2. And I also don't use it for over-mature eggs that I've forgotten here. And also not for IVM eggs, meaning prophase 1 the day before, and then you wait the day and it's M2. So definitely not the best option to use ionophore here. And I recommend to wait 1 hour before applying the ionophore at all, meaning it would give the oocyte a higher chance to finish the cytoplasmic maturation. So the effectors of ionophore potential are numerous, I would say, irrespective of the fact whether you do a ready to use one or if you make in your own lab. So it's the concentration. You have to be aware which concentrations you use. You can under concentrate it, you can over concentrate it, unless over concentration does not do that harm. Exposure time is critical, keeping in mind osmolality. So the shorter, the better. So maybe it's better to have 2 shorter pulses or applications than 1 longer one. The number of applications I will show you in the next slide and almost come to my end. The type of ionophore we already discussed, the quality of the ionophore we did, and the latency of ionophore application I also mentioned. So 1 hour delay right after ICSI before you go into the ionophore may give you better results, at least for those that were cytoplasmic immature before. So what would you do in case the ionophore treatment fails? So you could increase exposure time, although I see this a little bit critical. You could switch to a combination of 2 ionophores, and by doing so, bringing down the overall concentration. You could choose a more invasive approach by directly injecting calcium chloride together with an ionophore application. You could use recombinant PLC-CEDAR, which to my knowledge is not available yet, but I think all the companies are working on it. But what we would do or recommend is to switch to twofold exposure of ionophore. And this is the publication that we did. So this is the control cycle. These were the cycles where the ionophore with a single application had almost no effect at all. But by using it twice, we get significantly better results. So you see here, the same here, but in between the two stimuli of 50 minutes each, we have a 30-minute rest in your culture medium. And then we do the washing process, and then we go on with the culture. But I would actually draw your attention to the last sentence that I have here. So do not use the same ionophore drop for both applications. At the beginning, we did use, to save costs, to be honest, we used the same drop, a large drop. Nevertheless, the outcome was worse for the second share of oocytes that went in. So the second time you went in the same drop, we had those, it looked like a little bit of a shrinkage, and definitely fertilization was poorer then. And once we used a new drop, a fresh drop, also pre-equilibrated for 4 hours, of course, then the outcome was much better. And this is what we did here for the study. So we had some learning curve, that's for sure. Yeah, this one I think we can skip because Evrim already said that it's pretty sure that it's a safe technology, although one should only use AOA with a proper indication. This is one poster that we presented last year at ASRM, showing the first live birth with a ready-to-use ionomycin. So the company I work with is now testing a ready-to-use ionomycin. So this will be tested in Ghent, and we actually plan a prospective study. So would be interesting if one of you who is already working with a ready-to-use calcimycin, for example, could join us, but this is up to Björn Hendricks to decide. And last but not least, I'd like to show you this slide, and this is what I would recommend, the flow chart. If a patient has no fertilization with IVF, with conventional IVF, of course, all of us would do ICSI, or most of us would do ICSI. And if with ICSI you have no fertilization, then it depends on the number of oocytes. If you have 1 or 2 oocytes, well, then it can happen, of course. But let's consider we have 5 oocytes, 6, 7 oocytes, no fertilization at all. Then you have to do any type of artificial oocyte activation, as shown here. And if you then have no fertilization, then I would either wait for recombinant PLC-SIDA, or I would send the sperms and the buccal swipes to Belgium, and they test for PLC-SIDA, and they also test for V2 in the case of the lady. And they would do a MOAT, a MOCA, a HOCA, meaning they bring in sperms to mouse oocytes or to human oocytes donated for research, and then they have a look on the activation rate. And if then you have no fertilization at all or no activation with the MOAT, then definitely you know whether you go for sperm donation or oocyte donation. And with this slide, I thank you very much for your kind attention, and I'm so sorry that it didn't work as supposed to.
Thank you, Dr. Ebner, for this insightful presentation. So now we will move on to the panelists so they can start the discussion and convey the messages and the questions from the audience. The panelists, Nagam, Alia, Khalil, and Kerem, the floor is yours.
Thank you, Thomas. Thank you, Evrim, for this enlightening talks. The information were really valuable for all of us. I'm looking for the questions. I cannot see any question from the audience, so maybe I can ask both of you about the safety concerns of this procedures in terms of epigenetic consequences and any gene alteration, if there were any thing reported in live births from activated oocytes.
Yeah, if you don't mind, Evrim, should I start?
Of course, Doctor.
Thank you. Yeah, because actually I've read 2 papers on epigenetics and ionophore applications. So ionomycin and what happened to the epigenetical status, to the methylation of the genes. And there was one paper in particular, both papers were actually mouse models, but in a way they were a little bit alarming. One said at blastocyst stage there is no problem at all, but if you do cleavage stage transfer, you have a higher risk to have a different methylation pattern. For me, this is not particularly logical. Nevertheless, I'd like to share this information with you. And the other one did found some changes in methylation, also in gene expression, but yeah, nothing harmful, I would say. But this is something that we should keep in mind. And again, I'd like to stress that we should only use it if it's indicated. So I've heard of countries that use ionophores in, I don't know, 80% of their cycles, which is actually not the way to go. And then it's not wondering that you don't have that effect. For the ready-to-use compound, there are in literature, most of the publications are from our group, but in at least 300 to 400 live births and only 2 malformations. Meanwhile, 3 malformations out of, I think, 800 or 700 babies born, meaning it's 0.6 is the malformation rate. And that's actually lower than with our normal population, where we would expect 1 to 3% approximately. Yeah. So to my best knowledge, it's relatively safe, I would say, and we do, report all malformations that we have, if we have them. And I hope you also collect all the data. Without collecting data, we can't make progress.
Definitely. And is your routine to have consents from the patients just for protecting the safety of the patient?
We did have a consent for a very long time, but according to our ethical committee, once you have publications, then the ethical vote stops. So you provide them with the original peer-reviewed papers, and we had 3 or 4 of them. So they, on one hand, it was good because there was no need for the consent form so far. The other problem was they forced us to use the ionophore at oocyte stage, also for those where we tended to do it a little bit later, for those with the development problems. Yeah, so it's a good thing and a bad thing in parallel, but no consent form so far. But for the ionomycin, of course, we do have it.
The same for EBRM, for electrical stimulation?
Actually, while we are performing electrical stimulation, we also make some validations with the chemical methodologies as well, and we compare the results of different type of chemicals. It's been so long, but at the end, electrical stimulation became a routine protocol for us. But even for both for electrical stimulation or chemical stimulation, there is no any standardization. We are still talking about the concentration, duration time, and the biggest disadvantage of chemical methods is a long exposure time, according to me, 15 minutes or 30 minutes. But the electrical current, the major limitation is the users are not widely extended, and making multi-center study was not easy. But with the new and nowadays users numbers are getting higher, and hopefully multi-center studies can be released. But for the electrical current, we gave microsecond levels electrical stimulation. Duration time is very, very quick, but still we also use chemicals during these stages. And there is many gray side zones actually, but for both techniques, I think we need to solve some problems, and we need to focus on the standardization part. As I said, for this purpose, multi-center, multi-country studies is highly important, but as Thomas said, not easy to obtain ethical permissions, and making multi-center studies not easy due to different legislations of due to regulations of different countries. And but we should remind that this is end of the line treatment. So when we consider a TFF case, until we give activation treatment, we don't obtain any fertilized egg. So we need to, according to me, the major indication is total fertilization failure. As I said, oocyte-borne problems can be solved via oocyte activation, but sperm-related problems still is not easy to manage.
Thank you, Thomas. Thank you,
Thank
Efren.
you.
Alia?
And Negam,
Can
we
I
have
comment?
some questions. Nejati, yes.
Yeah, if you allow me, please, I just
Yes.
want to express my feeling. I'm so happy to see this collaboration, and here is to our continuing success and to try to express our knowledge and experience. It's also incredible to see our field, how it's evolving, and these are the forefront figures for us to foster our education and growth. For me, I have some practical questions. Actually, I'm using the calcium, the ready-made calcium ionofluorescence, maybe sometime now. Regarding the preparation, maybe it's more practical question. It was mentioned in the leaflet and also with Dr. Thomas that you should prepare it maybe 4 hours. Is it okay to prepare it overnight, like the day before the injection, or it should be limited to this time? My second question is, we can see that the calcium ionophore, maybe it's widely used in the labs, maybe because it's easier to use and to imply to the systems. While the electrostimulation, I'm not really sure if I know anyone using it nowadays or in our area. So is it really effective, or is it easy to introduce this technique in the labs, or does it need special skills, special requirements, and maybe a special training?
Dr. Thomas? For the electrical stimulation part, according to me, standardization of the oocyte activation can be more easy with that kind of device, but still studies are accumulating, and many users don't release any publication. They are using their own laboratories, but they don't release any data. This is the other limitation. There are many embryologists who use electrical stimulation with different instruments. However, they don't share their data via in the literature or via conference speeches. So Dr. Thomas, it's been so long, he has been focusing on this specific area, and I think I checked the last 3 years, 46 publication is available. For the electrical stimulation, 19 of these publications are 2020. It's published in 2020 and between 2022, and the publications numbers have been increasing, but still the users should release their data in order to see their results. But as I know, we don't have any neurological or developmental problem until today. It's been so long, and we have many, especially for the TFF cases. Unfortunately, I couldn't collect all the data due to limited time, but the data I have given is not complete one. We have many cases. As I said, we also give service to other IVF centers as well, and they have also their own data. And I know that there is no any systematic or phenotypic problems until now.
And regarding your first question, I do see no problem to incubate it overnight. At least then I would, try to aspirate and release the oocytes, bringing it in just to give it, to avoid a gradient. But even if there would be a gradient, the ionophore would meet the oocytes on the bottom of the dish of the drop. So we do not do it because actually it's always after ICSI, meaning that we do it in the morning just to be on the safe side. And I have no experience with having it overnight. So it would be overnight plus 4 hours. Yeah, but in principle, it shouldn't be a problem.
And the 30 micron, it should be only per one oocyte per one time, right?
Did you say current?
I mean, if you will use the one drop of the 30 micron of the calcium ionophore, it should be for one oocyte and only for one time.
Well, I can't tell you the embryo density that is, the maximum of oocytes that you can bring in a 30 microliter drop. I would bring up to 5, I would say. But if there are more, I would increase the drop. So there is no volume per embryo. Yeah.
All right.
But I would not use the same drop. This is something that it is for sure.
Okay, understood.
And if once you open the bottle, you have to discard it after 1 or 2 weeks, depending on your SOPs. Anyway, so I would not keep it too long. Yeah, but up to you, of course. But don't freeze it because this is not going to work.
No, yeah, of course. Yeah.
Can I have a comment?
After
Yes,
Necati,
try.
I can go.
Okay.
Yes, sir.
I mean, so one of the ideas of this webinars or the meetings is that discuss the tips and tricks. And Thomas was very right on emphasizing the way that the media is produced. I mean, ideally, I believe that we all should use an industrial, ready-to-use and quality controlled product. I mean, otherwise, all of us have a different way of preparing the product, even if it's very simple. As you said, it's very simple. It's like a dry powder. Maybe we can just, let's dissolve it in a solution. But I just checked just one article published in 2021, and while you were speaking, and in that article they mentioned
to me.
What?
You're not allowed to do literature
research.
No.
I'm a multitasking person because I just remember something and I just checked the article. It was meant to be a good article, and they were saying that they just dissolved the product in a culture media. They didn't mention any DMSO. So that means that even the product preparation is simple, but it's strongly prepared, so that maybe you will not be getting the expected results of this kind of applications. So if you look at the published data so far, it looks like that you are comparing oranges with apples. I mean, from the in-house production side. So ideally, we should all be maybe using the commercially available product to compare the results, which one is better, which one is worse. And also, I believe it's applied to the electrical stimulation part as well. It looks very simple, but we have oocytes with different quality. Should we use the same, let's say, frequency or duration of the same impulse, direct current or alternative current? Whether we are overdosing the oocyte, maybe we just degenerate the oocyte, I don't know. But in the past, I used to do some electrofusion experiments, and I remember that I had to use a very, let's say, high osmolality product to create this currency. So even this product can be very harmful for the gamete cells. So which means that there are a lot of things we have to perform to optimize the way that we perform. But it looks like electrical stimulation, it looks a little bit, let's say, handy from my point of view. But again, we need to have a large and randomized and comparable studies to see which one is giving us better results.
Necati, actually, exposure time and the osmolality issue is related with the if you do fusion, it should be very increased amount. But if for the oocyte activation, we don't use a high osmolality media, and additionally, achieving optimized protocol is not easy. Different electroporation instruments needs oscilloscope in order to check the in order to calibrate the system each time. We should also overcome this problem. Some of the instruments you don't need to use oscilloscope as well, but at the end chemical activation has been using for a long time. Many embryologists are highly experienced on it, but still I can hear that they are still asking the time, duration, chemical type. Even they are highly qualified, even they perform a lot of cases, they still asking for the protocol and the chemical used. I think this topic is open now, and we will do more actually.
Halil.
I totally agree. Thank you for this for the wonderful speeches. I mean, especially when it comes to Thomas's speech. I mean, I tried calcium ionophore ready to use one, and I couldn't make it work. And it never occurred to me to agitate the sample. I mean, I never thought of it. I thought it would be homogeneous already, even though I know that it has the MSO and the molecule itself is hydrophobic. I never thought of it. So I think it's been an eye-opening session already. So even the experienced ones can make silly mistakes. I mean, it's totally normal. There have been some, comments and questions coming from the audience. I'd like to outline them first. Seda Erdem asked if we can use these technologies in immature reproductive cells, which was already actually answered in Thomas's speech. So I think we can skip that. Odei Alka Vasma, I don't know if I pronounce it correctly, has asked about the electrical stimulations safety and its applications in our labs, which was already covered as well. Jihan Chakır from our board asked if we needed consent forms for ionophore applications, which was already covered as well. I'm just going through them so that we can go over everything in detail. Our colleague Aishin Akıncıbak is asking, does a double ionophore application improve the outcome of cases in which single ionophore application was unsuccessful? Thomas, can you please elaborate on that one?
Yeah, it did in our hands, but of course, not in all. Maybe some, I can't give you the exact number. It was something like 40% had then a pregnancy or at least an embryo transfer. So, but 50 plus did not have a success. So it means it's not the gold solution. It's the only thing that one could do before the ionomycin is available, for example, which I consider to be more potential. And coming back to your point, you should not forget, Halil, that you deal with severe male factor. So you're an expert for those cases. So I'm not sure if if you could expect, at least in those globosospermic patients, such an effect. I don't know if it's steering or agitating is all you, and then it works. So it's so hard. It won't work.
I just wanted to point out that this is a very nice tip coming from your side as an expert. I think it can be highly crucial. Maybe we are using the product completely wrong way. So I just wanted to point that one out and underline it. Can I ask a question before?
May I ask something to Dr. Thomas, please, Khalil?
Yes, of course.
You have mentioned that the amount of the calcium in the culture media is also crucial for the success of the application. But do we have the information about the amount in almost all companies do not represent a concentration. So how can we decide how much or how long we have to subject the oocyte to the chemical ionophores?
This is a very good point, and actually it's a pity, and that's why Esri, set up this culture media task force that all of a sudden after 2 years stopped. So they approached the companies clearly asking for the ingredients, and there were only 2 companies out of 6, 7 that were actually willing to do so. And those were the KSOM people, and most of the global media or universal one-step media that we use nowadays are all based on the KSOM. And for KSOM, you can get all the information. So I think this should be, a feasible option to get this information. What I didn't mention is that if you artificially add calcium to the culture medium, that you dilute the ionophorin, if you do it in a homemade way, then there is not a higher effect. So if you think it's not enough calcium, that you can't add it outside the cell.
Yes, and we have some other questions. May I go on, Halil?
Can I just squeeze in one more question before continuing? I'm asking to both speakers and of course to the panel and the moderators as well. How should we define success after artificial oocyte activation? Should we still consider 1PN formation or maybe 3PN formation after AOA success? And let's say that if we have this, how should we proceed to check if they been normally fertilized or whatever? I'm just trying to, because I see this on a daily routine basis. Following AOA, I'm getting a lot of 1PNs, maybe. And should I define them as success when it comes to artificial oocyte activation? And regarding the IVF success, how should we proceed and continue with those cases?
That's a big question.
Evrim, please.
Koray also asked a kind of question, as I see from the chat box. Yes, but it's not same, but very similar. I was checking the data I have prepared, and as I said, TFF, global, totally motile, and low fertilization groups were evaluated, and almost 5 to 13% abnormal fertilization ratio was observed. So mono-PN, syngamy, multi-PN abnormalities was observed, and distinguishing mono-PN with the syngamy is not easy. According to me, making aneuploid screening may be a good option to check the embryo, not only embryo quality, but also genetic results. It can be a good outcome. We have a kind of data, but as I said, I couldn't prepare for the speech. But mono-PN ratio is not much higher than the other abnormalities like multi-PN, as I said in the data.
Yeah, same here.
Thank you, Thomas.
Yeah, same in my lab. So more or less normal. KPI 1PN is more or less normal. Normal means 3 to 5% maybe, according to the KPI paper. Definitely, I would count 3 and 1PN not as a success. So I would strongly recommend to focus on the two PNs. Even there may be some 1PN that actually are fertilized, but since we can't prove it, let's focus on the 2 PNs. And there we know that that in the total fertilization failure group with our studies and the one from Markus Montag using the ready-to-use compound, we have something like 48 to 52% fertilization when we had none before. This is less than with ionomycin from the Ghent group. They report 65 to 70%, which is significantly higher. But what they also do is to inject the calcium chloride right into the cell during ICSI, which I'm not allowed to do in my country. This means you never know whether this is this calcium they brought into the cell or is it the ionomycin, but in combination, this is 70% is what you can expect. So, and you can compare every method or the effectiveness of a method. If you have 45% with calcimycin, maybe 65% with ionomycin. And if you're below that, if you have none, then it's not a success. The success definitely for me is not fertilization in particular. It's rather if there is an improvement to the previous cycle. In any case, could be fertilization, embryo quality, or blast formation.
Thank you very much, Dr.
Can I ask a practical question? Yeah, Thomas, why don't you use like a 4-well dish with much higher volume of media? You know, why do you stick with like 30 microliters?
I don't stick with 30 microliters. I use 100 microliters. And to be honest, our doctors, we have I would say a mild stimulation. So never ever we have more than 10 eggs, maybe 15 sometimes, except the PCOS patients. But in general, a lower number of oocytes, so that it's never more than 8 that I bring in per drop with 100 microliter. And if I have more, I prepare more drops. Yeah, but easily you could use, 200 microliter, then it's not a drop, then you cover the bottom of the dish, but you should always keep the costs in mind. So it should be cost effective as well. But if you save in the wrong place, you get a negative result or a worse result as you could have. And that's why, yeah, you have to find your way through the culture conditions.
Because I mean, I thought about your comment on using the same drop for multiple oocytes. I was thinking about like dilution effect that you bring maybe at the media from the previous drop, so you can minimize it with a much larger volume, maybe.
Yeah,
I was just thinking.
But it should not be like having one bottle of this compound per patient. I think it's 1 mil. It's 1 mil, so 5 patients with 200 would be possible. But what I experienced is if I used a one-time application and had more oocytes and had only one dish, the second half or the third third always was worse as compared to the first one or the second one.
What was the concentration of ionophore in this ready-to-use media? Is it 10 micromolar?
It's not it's a secret more or less, but it's I can tell you it's more than 10 mic.
More than 10, okay.
Yeah, it's more than 10. And Nikki Faraki, for those of you who are interested, Nikki Faraki in her paper, she calculated based on the literature that we all published. And she made a pretty good estimation. But the thing is, if you keep that in mind, you could use 25 millimolar and no further effect.
Yeah. So it's less than that.
May I ask one other practical question to Thomas, please? We have talked about the indications and possible cases where which one of the ionophore is more successful than other. and the timing of the application, the volume of the medium, and the volume of the ionophore solution. And we have a variety of instances where we cannot actually apply variable solutions. We can only use the commercial available product. Can you give us, please, a basic application procedure which fits most?
Well, this is a hard question, but this, if you say you use the ready-to-use compound, because I have only experience with that.
Yes,
definitely. Sure. Most babies born healthy have been cultured, ICSI, immediately go into the ionophore for 15 minutes, and then 3 washings, and then you go to culture. And for those of you who are still nervous because of the formula that I've shown you, please, you should actually know that due to the very high molecular weight, it's 500 to 700, depending which type. So it's a very large molecule. It will never enter the oocyte. So it makes a construct with the membrane, so that the calcium is transported, the molecules are transported from outside to inside, but the ionophore itself never enters the oocyte. So this is some of our colleagues have this in mind, that the ionophore is sort of toxic. Mm-hmm. Once it's in the egg, it never reaches the egg.
Yes, that opens the
membrane permeability. Yes.
Yeah.
Yes.
Yeah. It does something. It's a complex with the membrane, and then it makes a sterical change, and then the calcium. So it's literally is from extracellular brought into the intercellular part, but only there.
Yes, sure.
Okay,
thank you.
Okay, I think we have a bunch of questions from the audience. Dana Khalifa is asking about if there is any studies available for using calcium ionophore routinely to ensure and enhance fertilization even without TFF history.
Well, I strongly advise not to do that. Okay. This is the official information, and I do not, because then you are more disappointed than you are happy. Yeah. And we did use those techniques for borderline cases, and if there is no effect, with every effect that you don't see, you get more frustrated. So maybe you can bring up your fertilization by 2% or so, but this is not worth the risk. Yes. Not at all.
I agree 100%. Zafer Nihat, hopefully I'm saying the name correctly. He said that I have very limited data, but I want to share my preliminary results just for contribution. Patients having lower number of blastocysts even after ionomycin were used, had better results when used electrically, I think. This is a comment. Aday Qawasmi say that to Dr. Thomas, what is your thought about rescue oocyte activation of unfertilized oocyte using calcium ionophore?
Rescue fertilization means after it was not after 1 day to bring it again into ionophore. Is this what is meant?
Yes, there are 2 questions about this.
Well, there was this guy called Xu from China, and I think they did something similar. Mm-hmm. But there was also one paper in ABM Online from a lady from the US, and she did not see a benefit, but she used 5 micromolar, as a too low concentration to see any effect. Okay. I have no experience, to be honest, but at least I'm aware of 2 papers that tried that. Okay. One with no effect, and one did see some effect.
Okay. So, Mataza Ahmed, I think this is an answer for your question, because you are asking about also rescue XC. Kuray, he does, saying, I'm wondering, mono BN rates with electrical activation, did you have experience any tendency and increase mono BN rates with electrical stimulation? Thanks. I think this is for everyone.
I think we responded
Yeah,
this question.
we covered this, yeah.
Yeah.
May I have a question, please, if you allow me? What about if we combine the two techniques? For example, if the ionophore didn't work out, so next time we can do both electrical, chemical and electrical. Do you think it's worth it?
Sorry, in which stage do you mention?
Like if you have any experience with combined activation, chemical and electrical.
Combined methodologies have been publishing, as I say in the literature. The different chemicals have different beneficial sites, and researchers want to use these advantages by making combination of the chemicals. But I didn't see any combination with electrical and chemical ones. I also wonder, Dr. Thomas, how about the cleavage arrest cases? Do you think that activation methodologies can improve cleavage arrest embryo development?
Well, we experienced that. It was a multi-center study, not only in my clinic. It was five or six clinics, and all the clinics did see some benefit. The only problem is it was a very inhomogeneous group. So it was one group with complete arrest in the previous cycle. It was one group with a very low blastocyst formation rate, and a third group with a delay of 24 hours in development. So it's way too inhomogeneous to take conclusions or to draw conclusions. And this most probably is the problem with the recent literature that did not find any benefit. First, we have to identify what is developmental problems, or what is, embryo arrest is okay, but we're talking about developmental problems, and this is a very vague definition and maybe a summarization of different underlying problems. And we take it like a shower and bring in ionophore or electrical activation. And for some, it's the optimal way, but the others, it's completely in vain. But we don't know it. So to avoid the risk of not having done anything, we use it on too many. It's completely overused, particularly in my lab, I would say. I'm ashamed. So second time, I'm embarrassed. The technical issue and the rate of ionophore usage in my lab is also almost 20% of the patients.
Really?
But we do get a lot of patients from other clinics because of their problematic situation. Yeah.
Can I rephrase my previous question, Evrim? I mean, assuming that, let's say, 5 clinics or 5 labs have the same electrical stimulation machine, can we use the same setting for the oocyte activation for all? Or each clinic should have has its own, optimization.
In the recent status, we set a standard settings to the instrument. Each embryologist use same settings for oocyte activation. But if they want to use this instrument for different aim, like monoclonal antibody production or fusion event or other mitochondrial recently popular events, they need to change the adjustments. But they cannot change by themselves. For the oocyte activation, they all have to use same
standard. Okay.
Yes. Due to eliminate the oscilloscope usage. That kind of standardization is very important because mouse assays have been held and the optimized protocols have been set. So we put a very standard adjustment settings for this purpose.
Can I just quickly add something?
Of course.
Thank you. I agree that I think using electroporation, the electrical stimulation, is somewhat more standard in labs. because you're using the same pre-selected protocol, and everybody is using the same method, and it's basically a given amount of time of given amount of voltage of alternative current and direct current. I got the privilege of using an electrical device with the oscilloscope, but I don't use it for calibration purposes. I use a pre-selected and predefined protocol for artificial oocyte activation. So it's all set. But when I check my data, even my media amount in the probe is showing differences when it comes to resistance of that current. So in the ohm outcome, let's say. So this might create some unwanted, unstandardized outcomes. But the advantage of the system, I think, is that we all use the same media. So for our artificial oocyte activation, it's a made one, homemade one, let's say, with given amount of mannitol, calcium, magnesium, and whatever there is in the media. But it will be always the same. So it won't be there won't be differences coming from the media, as Thomas showed. The area under the curve is drastically different with Vitrolife or Sage or whatever the culture media company is saying. So I just wanted to underline this. But the way we put the media and the amount of the media in the probe is going to change our resistance of that electrical current.
So you are not using,
also have a role in it.
You are not using, commercially available culture media. So you prepare a homemade media with higher osmolality because you're using mannitol in it.
Yes, exactly.
My final point to Thomas. Several years ago, you talked about modified ICSI. What's the value now? How do you implement it? Are you still using it in your lab?
Yeah, this is a good one. Well, what to say? We did it. We did this technique because the Tesaic approach was very invasive with 21% degenerated oocytes. Then we were very proud that we could improve it. But if you look on our papers, and there's only one in an English-speaking journal, I think the degeneration rate was also 8 to 10%, which is also unacceptable. Maybe not according to the KPI paper of Alpha and Esre, but for me personally, we had one patient with 2 oocytes and both degenerated, and then I stopped and looked for other approaches, and that's when I approached the company to produce us an ionophore based on the recipe of Markus Montag's work at the University of Bonn. So this was this was my key, experience in a negative way. So this lady was really desperate afterwards. And she did not have fertilization in the center where she went then. And yeah, what should I say? I changed my approach and I didn't use it. But colleagues from Vienna used it quite long, and they were happy. And they do combine now ionophore with this more invasive ICSI technique, and they are happy. Not for all patients, of course. So this would, coming back to one of the questions, if it would make sense to combine it. So why not? The more calcium, as long as not at the lethal value, because too much of calcium is also not, what we want.
I think by combining, Naga meant that the sequentially using of the technique, I think. So if one cycle, if the calcium ionophore doesn't work, then the next cycle, maybe we can try electrical stimulation, right, Naga?
Yes.
Okay, sorry. I thought it should be, doing the electrical activation, then bring it into ionophore at the same cycle, because this is what the colleagues in Vienna do. They do an adapted, modified ICSI, and then they go to the ionophore.
So the oocytes either die or fertilize.
Yeah.
No other choice. Okay,
Yeah.
great.
So,
Do
any
we
more
have
questions from the
questions?
audience?
Yeah.
I don't think so on the live
checking.
chat. So
Okay.
let's wrap
So,
up.
yeah, it's been nearly 2 hours. Oh my God.
Yeah.
So I want to take like my last opportunity and to thank our privileged speakers for participating in this first Tech Talk activity for the service of embryologists. And also I want to thank the KED and MEFS executive teams for making this happen. Nejati also.
Thank you, guys. Thank you for your
Sure.
contributions. Thank you for your valuable comments and presentations. I hope to see you soon in another Tech Talk, as Fadi mentioned, with another stimulating topic, hopefully.
Yeah, we hope
Okay.
so.
Shukran. Teşekkür
Okay.
ederim.
Shukran.
Thank you.
Thank you very much.
Bye. Bye.
Thank you.
Bye-bye.
Thank you.
Bye.
Thank you very much.
Bye-bye.
So far, so good.
We're live on YouTube. We're still live.